Well, thank you very much. I'm very pleased to be here and participate in this conference, which I think is a very, very important topic. And so what I wanted to talk about is, design in the computational age, and the part of the computation I'm going to talk about is it's based on a couple of premises. Two premises. One is that geometry is the intersection of architecture and structure, and it's very, very central to structural engineering in general. On this building that I had the opportunity to work on in London quite a while ago, it's over by Liverpool Street Station. If you try to describe the structure, you will be describing the architecture because they're identical, and you'll do both in geometric terms. And so I think design tools which are based on geometry are very essential. And then my other premise is that structural designers are generally pretty visual people, that they understand, they see things in a visual sense, and even a lot of the computational tools such as Kangaroo and the like are essentially are in response to that, the visual nature of engineers. And so first of all, I want to do a really quick kind of survey of architecture engineering in the past, shall we say people pre-computational age. And here you have, I'm going to go all the way back. Let's go back to the Romans. I could go back to the Greeks, but they only had beam and post. And the story of architecture is written in a language where the words come from structure. And the technology and the geometry that the Romans had, were, of course, the arch and the dome, which created architectural opportunities that and actually very good structures, very, very efficient structures to be built. You move forward and you see the Gothic structures with their incredibly expressive structures, where we know the force is in the masonry, because if it wasn't, it would collapse. There is no rebar to hold this thing together. It is the forces of the structure itself. And so I think this is a good metaphor for what we need to do. And, you go up to Cambridge and you go look at the chapel there at King's College, that is held together by gravity. And some of that is only 4 inches thick, 100 millimeters thick structure that where the geometry and the design was done with enough precision that it is the right geometry. I mean, a little bit more closer to our modern era, but still about 100 years ago, the work of Guastavino with his vaults, where he was able to build these very pure shapes with geometry, but also with very little false work, and that's an important thing. Constructability was part of the design, as it was for all these people. Sukhov with his hyperboloid tower in Moscow, so did a whole series of these things, are, I think, very, very, very important. You look at Maillard, and I'll come back to Maillard in a minute here from a design metaphor point of view. Very, very important work. And then Torroja with his shells, or Luigi Nervi with his incredible geometry that it was used in design, and Felix Candela with his work, and Buckminster Fuller, and Heinz Eisler with we made from the physical models. And so these are very, very important processes that I hope we can do as well today as they did back then. Diesta with those incredible shells, Frei Otto, which was done by he did with Ted Hoppold and Ian Liddell and Chris Williams together. This incredible structure that is out there. And what tools did these people use in this pre-computational age? They used theory, simplified calculations, experimentation, intuition. And so I think it's how can we do structures today that are as beautiful and as efficient as our predecessors, but even better because we have better tools. And I think there's been a fundamental change in how we design. I think that's what this conference is about. And so, in the past, it was a lack of computational power. It's kind of interesting. If you look at the drawings that Frank Lloyd Wright made for his proposed mile-high tower in the 1950s, he listed a series of names, of which about 12 names, of which about 10 of them were structural engineers, and 3 of those 10 were professors, one from Berkeley, one from Hardy Cross from Illinois, and a professor from Princeton, all 3 of whom were doing work in computational theory of the time, how to calculate indeterminate structures. Because Frank Lloyd Wright, architecture was limited by his engineer's ability to calculate. And so today we have almost the reverse problem, is how to harness the computational power and to use it to create great structures, good structures which are low carbon, efficient, and beautiful. And so and what this conference is about is, I think, very important, is the harnessing of this computational power. Now, Lee Frank spoke earlier about in the design process how at the very, very front end of the design is the most important phase. And to do this kind of design, you have to have insight. And so, are we creating tools that give us insight? Because the purpose of computing is insight, not numbers. And so as we get these things, I find can we create tools that give insight, but are also accessible? You don't have to be shall we say a mathematical genius or a programming genius in order to use these tools, but can they be accessible, but also provide insight? And I think when you get into conceptual design and you use some of these tools, I think it's perhaps more important to know why something works, as opposed to just what works. If you have a program or something that gives you a solution or gives you an answer, and you don't understand why that is a better answer, perhaps you need to look deeper, because once you understand the why, you can perhaps even change the problem. Because part of the conceptual design problem is a lot of times just changing the problem once you understand it. And so, can we create tools that give us more into why something works, in addition to what does work? And so, can we create visual tools for structural engineers who are visual people that can do that? I saw a presentation several years ago by Sam Joyce he's now at the Singapore University of Technology and Design. He used to work for Foster's office. And one of his jobs at Foster's office was how to present data to clients. And I found this chart very interesting that he presented, which is that, the most accurate things have to do with expressing information geometrically, in position or length. And one of the least accurate way of presenting information is through color. And quite frankly, all of our finite element programs that we use every day, we always display the colors. And I'm always looking over at where's the scale? What does this color mean? Okay. And how do I deal with something that's like blue-green? Okay. Color, so I think we need to perhaps get with psychologists and others and help us understand how to communicate more clearly to ourselves, the information we're trying to get from these conceptual design tools. And I also think it's very, very important that we recognize that design is not black and white. A lot of times when I work with architects, and I know we're doing some kind of optimization study of trying to optimize some parameter, that there's one right answer, but we as engineers know that's not true. That it's a body of gray, and that we that we're and so I think we need to have tools that don't give you the answer, but they give you they allow you to do explorations. They'll give you inspiration and perhaps, hopefully, even understanding. And of course, the term optimization is probably one of the most abused terms we have. Optimize for what? You know, certainly depending on what your criteria or how you do it or what you consider, you'll get, you know, very, very, very different answers. Okay, and not only, I want to talk about geometry from a point of view, not only is it the intersection of architecture and structure, it's hugely important to the environment. Here you have two structures. They're both cantilevers. They have a 3-to-1 aspect ratio, and the difference between the two structures there is geometry. A lot of times our structures in the world are controlled by deflections. The structure on the top needs 60% more material than the structure on the bottom for the same deflection. There's been a lot of discussion, as there should be in this conference, about embodied energy. I mean, think about it. If you start with say a geometry which is not so good, you're going to be limited. You cannot get beyond the geometry, and so I think, you know, this is a very, very important aspect of this whole design process. And actually, as we explore these geometries that we might see, we may end up with new aesthetics. Here on the screen, you see two trusses. The one on the bottom is very familiar. It's the Pratt truss. On the top is not familiar at all to many people, but is actually much more efficient. And when I first started seeing these things, because we were coming up with these through our research, that, you know, they were visually uncomfortable to me. But over time, you know, I've grown accustomed to them, and I actually appreciate them, you know, from not only an engineering point of view, from an aesthetic point of view. And of course, as everyone said, you know, the structure is a huge part of the day one, the you know, embodied energy of a structure. Now, when we do research, and for those of you who don't know my firm very well, it's Skidmore, Owings and Merrill. We're architects and engineers, and we have several groups in the office that do research, and mainly on a volunteer basis, not really in dedicated departments. And for a while, you know, we were throwing away terms, and everyone would say something, and everyone misinterpreted what they were saying. So we made this little picture, a diagram for vocabulary. So you have that gray rectangle there is the design domain where one can have something. And then at the top, you see the term topology. And by that, we take to mean what is connected to what. And you see at the top there, there's two figures that have different topologies. Now, once you take that topology, you can then, like what is connected to what, you can then shape it. And that's what you see in the middle line there is shaping. And then finally, you can size the elements and the joints. Now, sizing is absolutely essential. We have to get that right, but that is not where you're going to make the big difference. If you look at that cantilever truss I had a few slides ago, I don't care how good you are at designing that connection. I don't care how good you are at designing that member. You cannot get beyond having the wrong geometry. And if you look at topology and shape, you could say, what is that? That's architecture. So the engineer needs to be involved in the very, very beginning, in the conceptual phase, to be sure you have a good geometry, which is meaningful and correct. And so part of it, we need to think and design. We need to think geometrically, in my opinion. Okay, we need to think geometrically, and we need to design geometrically and get geometric feedback. And I find that this is very helpful in my designs. You know, when I worked on the when I think about you know, the Burj Khalifa, when we worked on that, you know, it was all about geometry and basic engineering mechanics. You know, these super tall buildings are just giant beams coming out of the ground, and we calculate the geometric properties of it. Like we even calculate the radius gyration of the building. And I have a plot on my office locked up downtown because of the coronavirus. Anyway, so let's go way back. Let's go to the scary-looking man from Scotland named Rankin, who did some absolutely brilliant work. He was the Regis Professor of Civil Engineering at University of Glasgow, and he wrote an incredible book, which you can is a Google download, in 1858 on the Manual of Applied Mechanics, and it has two parts. The first part is the theory of structures. The second part is the theory, which are things that are not supposed to move. And the second part of the book is the theory of machines, things that are supposed to move. And it's very interesting. It has also a very interesting lecture on the harmony of theory and practice, so I urge you guys to download it, and I think you'd be fairly impressed by what our ancestors knew. And in there, he has this little chart about how to do graphical design. And so here is an example where you take a series of loads, applied loads and reactions that are in equilibrium. And what he urged the user to do is, draw those loads and reactions, put them tail to tail, put a dot on a piece of paper, and connect the dots to the tips of the arrows. And from there, you could create a structure which is purely axial. And what I like about this is that the designer is totally in control. The designer sees both the force and the structure simultaneously, and knows how to do this. How to manipulate if it doesn't like it. And so perhaps you don't like your solution. Well, and it does work, by the way. So this is from the wall at my office, and so you can see how this graphic technology does work. And so if you don't like that particular design, move the dot. Okay, let's say you want an arch, put the dot on the other side. And so through this process, the designer is in complete control. So let me give you one more metaphor here from going back, which is actually very, very currently important. Graphic statics and visual insight. One of our previous speakers, Laura Hannigan, of course, is an expert in graphic statics, or actually graphic kinematics. And so it goes back to another man from Scotland, James Clerk Maxwell, who wrote this seminal paper in 1864, which is where graphic statics came from. And you had this system where you have on the left you see something which you recognize as the structure, and it has certain notations. I won't try to get into much detail here, called Bose notation. And because every node is in equilibrium, there's a polygon that closes of forces, and that's represented on the right in the force diagram. And all these polygons fit together. And so if you wanted to know the force in a member, you would look at the structure on the right and figure out how long that line is, and that would tell you how big the forces are. And so you say, well, that's pretty crude. I mean, I got a fancy computer. I don't need an analysis. But the power of this system is not in that. It is as a design tool. And take this as a metaphor for the design tools that I think we need for conceptual design. Because, you can, so here, there was in the earlier presentation by Ian Poole, he talked about, splicing the top chord and changing the sides. What if you decided you're going to do this roof structure and you want all of the chord members to have exactly the same force? Rather than guessing the structure, you would draw the forces. And then from drawing the forces, you'd figure out how the geometry goes together. And then in the end of the day, you would have this kind of, let's say somewhat unusual geometry where all of the members on the top chord have exactly the same axial force. So you have this, your utilization factor that Ian Poole talked about is high for every panel. You don't have that. In his chart, he was showing that about 60% utilization is kind of average. Well, here you can get much closer to a much better utilization. And who would do something like this? Well, Maillard did it about almost 100 years ago, 96 years ago. He did this incredible building because he designed everything graphically. And earlier I showed this picture of the bridge. And it's noteworthy to see that it was designed by Maillard, and what you're looking at the bottom of the slide is actually his calculation, his computational design. where he put a dot on a piece of paper and drew a series of lines. And then as he designed the bridge, he'd figure out what the weight was, and he would adjust it. And he got this feedback loop between the structure and the forces to make a very efficient structure. And so, so the goal is here is to encourage, digital design for the visual structural designer. And going back, to the topology, shape, and size, just to remind you, and I actually would urge all of you guys on the conference, go back to that 3-to-1 cantilever with the point load, and calculate it for yourself. Show to yourself that why that one geometry has to have so much more material for the same deflection. And while you're at it, you also might notice that the tension load path, which is the force in the tension member minus the compression load path, which is the force times the length of the compression members, is a constant. That both of those trusses have the same difference of tension load path versus compression load path, and so that if you have inefficiencies, they're paid for twice, once in tension and one compression. And the load path is essentially equivalent to the internal energy, which we can say is also related to the embodied carbon. So how can we find new topologies and shapes? At my firm, we have like a menu of things that we've come up with over time. I'll speak about a few of these. And we use commercial software, which such as Altair, which came out of the aerospace and the automotive industry, and so. But we also use downloads, and I'm sure many of you have this stuff available. But when I look at this stuff, so I'm going to take something called Polytop, which is a SIMP or optimization tool, and I put this point load on there, and I'm going to grow a structure. And as I see it coming up there, what you should ask yourself is not only, here's an answer, here's the what, but you should ask yourself why. Why is it coming up with this? And what is the meaning that we as designers can use? I think it's very important for everyone on the call to be familiar with Mitchell trusses, because one of the things that was said earlier in Lee Frank's call is how do you have a benchmark? How do you know how efficient you can go? And so what Mitchell did is he came up with a series of structures here which give you benchmarks. These are, for a given load case, you cannot get less than these numbers. They give you the benchmark. They tell you. And so if you have an alternate design, you can say, well, how's the lowest? What's the lowest possible answer? And then, is my solution reasonable? Is it maybe, it'll be maybe not the most efficient, but maybe is it close enough? Are the benefits of fabrication or erection worth the investment? So I think it's very important for people to be familiar as much as possible with these Mitchell trusses. What's also interesting, if you look at this, if you look at each of those charts, the one on the left, it looks like half a bicycle wheel. The force in the rim never changes. If I look at that cantilever, the strange cantilever, the force in the outside core never changes. If I look at the truss on the right, the force in that outside cord never changes. It just gets turned. So my interpretation is that nature likes to turn loads gently. And that was an infinite one. This is a discrete one, and this is a response to physics. This is not capricious or willful. This is the shape that you'd find if you had a discrete number of elements rather than a continuum like the earlier solution. So what we do is we take a problem such as that, and we play with our tools, our conceptual design tools. And on the left, you might say it's where to put the members. On the right is where to put the holes. At the top of the chart, you have 15% solid. At the bottom, you have 85% solid, and you can see how you might get different ideas that you, as the designer, can then take into the final design. Or you have an unusual problem, and you see here, and all of a sudden you see a Mitchell wheel showing up, and then you have in the inclined space kind of a compressed logarithmic spiral that is in there. And by understanding that, you're not going to build this thing, but it may give you ideas for inspiration. And just playing with boundary conditions, and look at the arch in the upper left-hand corners. Notice that the hangers are not vertical, and that there's a little spur that grows. Why is it doing that? the why is more important than the what. And we've been using this in our designs. This is a project that was just finished in North Sydney, Australia, for Lang O'Rourke is, I believe, headquartered in there. And so we use these studies about turning the loads gently to inform the structure, which becomes the architecture. And it's also another talk, perhaps sometime. It's an interesting application. It's a steel-braced concrete building. Okay, another tool we like to use a lot is ground structures, where you have dots connected to other dots, and then you connect to a dot to its neighbor, and then to the neighbor of the neighbor, and to the neighbor of the neighbor, and then you just keep going. And then let's take the same problem we had before, and you start with a lot of members, you throw away the ones you don't like, and guess what? The Mitchell truss shows up yet again. And so what a lot of times what we will do is we will use multiple tools. We have a design space like this, or we have a solution that looks like this from one tool. We get a solution that looks like this from another tool. We go back and forth between the two. We get a cup of coffee, and then we decide what is it we should actually do, and then use your engineering interpretation, and perhaps come up with something that looks like this. And once again, it's a bit unusual, but it is very efficient. Here for equal deflection, one at the top gives you a benchmark. It tells you how low, what's the lowest you can possibly go. If you look at the Pratt truss at the bottom, it needs 68% more material than the benchmark, whereas this truss only needs 5% more for the same deflection. And so I think it's important to understand this thing and why turning the loads gently is what nature likes. Now, one has to deal with the alloplane buckling of that node in the middle of the web. Do you make one of the members continuous to resist it? But also, in fact, one of the members is in tension, the other is in compression, so it may be hard to be braced by geometric stiffness. And so, think about how much carbon you're saving. I almost never use Pratt trusses anymore. I do a lot of Warren trusses, or the truss you see in the middle. And of course, this applies to tall buildings. Here's a building that we worked on in China, that which takes this new geometry and comes up with a new architecture that is about turning the loads gently. Here's another project we have under construction in China that's based on this process. I was in London a few weeks ago, or I guess 2 months ago now, and I ran into Matthew Gilbert from Sheffield University, and he has this great little app that he just came out with, brand new thing. So copy that down, do a screenshot, and load it up, and it's one of my new favorite toys. But you can also do this in 3 dimensions, where you can grow a structure. Once again, it is the question is not what is the answer, but why is the answer. And what's interesting about why does the tree only have branches at the top? You're never going to build this, but you can learn about structural engineering. And that arch it's not a smooth arch; it's a funicular arch. You'll see that when it turns here. And actually, if you look at a 3-dimensional version of it, it's actually curved in both directions. It's both arched in elevation, but also arched across the cross section. This was a study that was inspired by Swiss Re. What would be the shape of a building where your penalty function is the wind load and you want to minimize deflection? Notice how it gets broader at the base, where it cares more about stiffness than it does about wind load, whereas at the top it tries to minimize the wind load. Shape. We talked about topology, and now this last one was about shape. Let's talk more about shape. You can do hanging structures. There was a very interesting hanging structure done by Foster's office recently, working with his structural engineers there, and for the proposed Mexico City airport, which unfortunately is not going to happen. That was where they had this beautiful hanging model. And, of course, we can do that computationally using force density or dynamic relaxation. And you look at what are the moral equivalents of these tools that are done These are what you're seeing on the screen right now are conceptual design tools of a physical sense. And one of it's interesting to me is the Fry Auto soap film. Now that's a constant stress structure, but the soap film has almost no weight. So one of the things that we've been doing is we've been working with what we call heavy soap film. How do you find a new shape where you have constant stresses in all directions? And so each of these, we call this the sushi tray. It looks, or sashimi tray. Each of these shapes look very, very, very organic because you grew them in the way that nature was. And so your design parameters are the amplitude of the thing and where it touches the ground. And here's an example where we took one of those shapes and made a grid shell where it's an optimal shape. All the panels are exactly, we call it the trifecta because it's a minimum weight. All the panels are exactly flat and all the nodes are torsion free. And you can only get this right in the conceptual design phase. So it's helpful. You know, we like to use the tools that are coming out of Zurich. There's a very, very good research group there run by Philippe Bloch. It's called the Bloch Group at ETH Zurich, which has some very interesting tools that are good for conceptual design. And they have an open source library program called Compass. Okay, now I want to take a little bit here and talk about taking some more old technology and bringing it forward. We're going to go to the Aries stress function, and I urge all of you pull out your old textbook and look up what the heck an Aries stress function is. And let me go back to graphic statics, and I hope all of you know how to do graphic statics. I certainly I taught it to myself maybe 10 years ago, and it just blew my mind away. Where I can see both the structure and the forces together, and realize that the geometry of the forces are designable. And so, as I showed in that earlier example, but an interesting thing, a very amazing thing that James Clerk Maxwell came up with, that if I take a self-stress structure, so I'm going to put that Rankine dot on my force diagram, I can create a funicular, and I've taken that structure, I made it into a self-stress structure. So the forces in that truss are the same as the truss I showed you earlier. But Maxwell made this amazing observation that for a structure to be in equilibrium, it has to be a projection of a plane face polyhedron, which is quite remarkable. And it turns out that all of the ridges are in compression, and all the valleys are in tension, and the change in angle between two faces is in fact proportional to the forces. As you look at this thing, because it turns out the mathematics of planar surfaces going around a node on a polyhedron is the same as the mathematics of equilibrium at a node. In structural sense of the two-dimensional structure. And so it turns out that this three-dimensional structure is the Aries stress function. And so we've been doing a lot of work in conceptual design trying to use Aries stress function. Here on the left is the structure, and on the right is the Aries stress function. And if you just showed me the structure on the left and asked me, is there any tension in that structure? I would say, I don't know. I'd have to run an analysis. But by seeing the Aries stress function on the right, I can tell you there is no tension in that shell, because the Aries stress function has a certain curvature in the radius. I can even tell you with certainty that there's no lateral thrust because of the way the Aries stress function meets the ground. And so this whole thing. And so you might say that the Aries stress function is like designing the forces. So this is something we've been doing in our conceptual practice later. And once again, this is one of many things that people can do. Recently, a year ago or so, we built this in Madrid, where we built this old technology masonry shell, was designed with the Aries stress function. And so that brings me to something that is currently locked away in the basement at the University of Westminster in London, where the coronavirus managed to isolate an exhibition we're doing, where we designed a shell using the Aries stress function. And here you see the form diagram, which is a planned geometry of the structure, force diagram, which is the planned geometry of the forces. The green is actually the shell itself, and the the red is the area stress function. And so what we did is we decided we wanted to take things that we know and like. We like compression structures because they're so shell structures because they're so efficient. We love glass as material, and then we said so we like these things. We like shells. We like designing with area stress functions and creating software to do so. And then we said we know absolutely nothing about computers, so let's set ourselves a problem where we're gonna design a shell using area stress function, build it out of glass, and build it with robots. And so this is, like I say, on Marylebone Road right now in London, locked away where no one can see it, other than Paul Shepard. Paul Shepard happened to see it shortly before the thing got locked down. So we had these two robots. We did this jointly with Princeton, University of Delft, TU Delft, and then Global Robots. And so, each of the robots has certain design ranges. And so in our structures, not only do we have to minimize carbon, we have to design to the constructability. And so, and not only that, these robots have elbows that can get in the way and knock down things. So we actually had to make a skewed structure that worked with the geometry. And so, here's the shell that we want to design and build. We design and we want to build. We looked at how to put together with tessellations. And because the robots can only work together on the center arch, and after that they cannot work together, so we pulled out Jack Hyman's book on the stone skeleton and figured out how to do this without formwork using a Nubian Volt technology. And so we started out, but the two robots on the left work together to build the arch with no false work. Now, as I was trying to point out to Paul Shepard, we're not trying to crack the market on glass shells. We're using this as a way to teach ourselves how to use these tools in a way. So we set ourselves this problem, and so here it is as it was built together, and as it comes together, and the robots were able to, with some supervision by a couple of humans, to build this glass vault. As I say, unfortunately, it's locked away on Marylebone Road there near Baker Street tube stop, but no one can see it. Okay, let me go back to this in a more practical design consideration. Can we do a visual design of the Great Court roof? This is one of my favorite structures of all time. A brilliant project by Burrell Hoppold. It was built by Wagner Burrell. Fosters and Partners were the designers. And Professor Chris Williams, who until recently was at Bath, or maybe he's still there for a little bit. He's moved to Sweden. He's in Chalmers University, and he also back in the day worked with Frei Otto and the like. Anyway, so he wrote these equations for the design team to use to come up with a shape that would do what it wanted to do. And a lot of this is based on the area stress function. So, I thought it was absolutely brilliant, but way beyond my reach as a mathematician. So, is there a way that we could come up with a visual way of designing this? And so a couple of years ago, worked with Tim Nugent, who's a fourth-year student up at Cambridge, and Professor Alan McRoby. Marina Constantato and I worked with them on coming up with a visual way to design this roof, where the designer could design this by designing the area stress function. So here's the grid on the left. On the right is a first approximation of the area stress function. And by designing the shape of the area stress function, I can design the forces. I know that there will be no lateral thrust, which was a critical design parameter in this building because they could not have lateral thrust against the old masonry buildings. And so by designing the area stress function, I can make a structure that does just what I want to do. Now, in the process, you maybe your first solutions aren't the best, and you have to some of the coordinates of the area stress function, but eventually you can come up with something that actually and you don't have to be a brilliant mathematician to design the Great Court roof. And so. Is that enough? I mean, so basically that was about coming up with equilibrium. We also need to have better feedback on the embodied carbon, the buckling values, the fluctuations, curvature, and the like. So can we create new architecture through computation and research? I think the answer, I hope, is yes. And for me, let me do another metaphor. Fry Otto and his team, they were able to create new, efficient architecture and structure through their research and through computation. This is an incredibly important photograph. Here you have the team working, who eventually worked on the Munich Olympics. On the left, speaking is, believe it, none other than Heinz Eisler. And next to him is Fritz Auer, an architect, and then Fry Otto, the engineer-architect, and then Georg Schleich, the engineer, and then Fritz Leonhardt, the engineer, and Rudolf Bettergemann, the engineer, and then Knut Gabriel, the architect, working together. And so my challenge to the audience is to create and use computational tools that will lead to new, substantive, low-carbon architecture. And with that, I'd like to say thank you, and I guess we will be taking questions.
So you mentioned earlier that we should take advantage of the geometry, and how these ideas have been used for hundreds, if not thousands of years for building structures. So my question would be that where do you think that modern engineering education went wrong and lost the focus on geometry in pursuit of calculation and numbers without a strong appreciation of form?
Well, I think we were seduced by the computer, which is kind of an interesting thing to say, the computational thing. And so I think it's about turning the computer around and making it making the computer computational power that we have more visual, so that we become more visual. And that and I think we're all kind of limited by our the tools that we were educated on. I was educated in more of the linear world, and so where your computer programs could not calculate a pendulum because it'd have a singularity and the program would blow up. And I love the Cambridge analogy of the three-legged versus a four-legged stool, where which do you need to design for the more load? Well, it turns out the four-legged stool, because if your floor is crooked, load at any one leg is somewhere between 0 and 50%. And so, learning to think beyond the limitations of our computational tools is an important thing. And I wouldn't say we went wrong. I think I just think we just need to be more aware of how can geometry change things. You might say that there's the two things: materials and geometry, are the two essential things that engineers should be thinking about at all times.
Moving on, how do you ensure torsion-free nodes in the grid cell example, whilst at the same time optimizing for the other parameters?
Well, first of all, you have to, you do principal curvature lines or the like, because it was a uniformly stressed thing. You have principal stresses are equal in all directions, and because of that. But also, if you have quads, okay. A lot of times you can just do that by if you have quadrilateral panels. If you have a triangular grid, you're toast. You're going to have, unless you're on a hemispherical surface, you're going to have twisted joints. But on quads, if you lay it out right and you lay it out in the right order, it's really quite doable to have non-twisted joints. Even if your surface is undulating and complex.
Okay, thank you. The Maxwell load path equates compression and tension, but compression members normally need more material to resist buckling. How do you adjust the load path to take buckling into consideration?
Yeah, you can do that in a couple of ways. You can have variable stresses. Now, it turns out if you have like a lower tensile stress and a lower compress, if your compression and tensile stresses are different, your geometry may not change too much. But if your compression capacity is highly related to the unbraced length, then you do. And so that just has to be part of your programming. You have to pull that in, and you'll and that's very much part of it. It will not be your minimum deflection structure. but it may be your minimum volume structure because of the buckling. One of the things I like about load path as a measure, like if we take the force in all the members times the length of all the members and add it up, is that it's a measure of the internal energy. And then sometimes on buckling, what I'll try to do is I'll try to actually proportion the members that are in compression differently to try to increase their buckling stiffness. But then there's a limit to how far you can go on that. And so, no, we also have, shall we say, knobs on our programs where we can activate maybe an adjustment for on-brace length for compression members.
Okay, thank you. How close do you think we can get to these ideal structural shapes with digital fabrication? And more importantly, how close should we try and get to them if we can be only 105% over the ideal shape with something that is straight?
Yeah, well, that 105 one, all the members were straight that I showed there. A lot of times you can get pretty close. What I find, what's interesting, if you take some of these Mitchell trusses and you make a discrete solution, sometimes just a little change in geometry or maybe an extra member will make a huge difference in the quantity of material. So a lot of times you can get pretty close pretty quickly with a very few tweaks. And then once you know the benchmark, then you know how far off you are. And a lot of times you say, well, I'm close enough. That if I try to get closer, it's actually diminishing returns in terms of the labor. Now, one of the things I liked a lot about what Paul Shepard said is, what if we designed in gold? I think that's very, very, very good idea. Because in nature, and you look at natural solutions, in nature, labor is cheap and material is very expensive.
Yeah.
And if we acted like that, we would, and so a lot of these forms we come up with look, to me, very organic, very nature, because like things you see in nature, not because we're trying to mimic what we see in nature, but because we're solving our problems using physics, just like nature designs with physics. If we design with physics, perhaps we will come with shapes which feel more organic.
Now, physics may inform these incredibly complex structures, but how do these structures translate into the real world? I guess it's a question about where do you draw the line of contractability, and is it ever possible to construct these optimum structures? What do you think?
Well, are you going to do a structure with an infinite number of members? Probably not. But one of my bosses always said, never propose a design without having at least one way to build it. And when we were working on the Burj Khalifa, we designed it to a construction technology. In fact, I want to say never, but I probably very close to never actually design a structure without thinking about how I'm going to build it, or how I'm going to do the connections, or how it's going to be fabricated. That's got to be part of the process. And so you have to take that into account and figure out at what point is it becoming too fussy, too busy. But but also on the other side of computation is the computer is incredible as far as the fabrication, particularly when you're in like timber and like where you can customize cross laminated timber. You can mill it to exactly what you want, or some of the 3D printing, or even in metal fabrication. With the computer aided process that people have been speaking of, that you can have some really quite amazing opportunities there to do things that were not possible or not practical by any terms just a few years ago. So I think we're in a new era where I think we're getting smarter and better structures and more ways to build them.
You also mentioned earlier that some more efficient structures imply new forms and new aesthetics. Assuming architects can be educated to learn to like them, what about getting the clients to accept them, and also getting the public to get used to it, and seeing new forms in the urban landscape?
Yeah, I mean, part of it is you have to, you got to be a salesman. You've got to be able to put your things across, but you also need to stay honest.
Mm.
I alluded to it in one of my first slides, the Exchange House there near Liverpool Street Station. And you might notice if you ever go by that, it's a building, it's a bridge. I think it's pretty good from a carbon point of view. It's only like 100 kilograms per square meter of steel, so very efficient. But you'll notice that each of the segments of the arch is a straight line.
Mm-hmm.
And it's not a curved line. People in nature are used to seeing masonry arches where the arch is a continuous curve. And so we had a big debate in the office, kind of spurred on a little bit by a lecture by David Billington from Princeton about the art of structural engineering, about the purity of the answer. And so we had a big debate in the office. We said, no, we're going to do what we think is both correct answers technically, but also aesthetically. And that year, the Financial Times, they at least they did back in those days, gave an award at the end of the year for the best building of the year. And they explicitly did not give it to Exchange House because we did not curve the arch.
Mm-hmm.
And they said that in the editorial. Now, go forward 25 years. Just a few years ago, it got the AIA, American Institute of Architecture, 25-year award. There's only one building in the entire world that gets that award every year, and Exchange House got it the first year it was eligible, and so we felt a little vindicated and if you look at it now, it feels natural, and so I think it is. You got to get it out there. People have to start seeing it, and then it becomes just like it feels natural to see a power line with a gentle curve on it, or if you hang a load on a clothesline, you expect it to be funicular, to have an angle change where the load comes in. I think we need to get these out there. They need to get built, and then it'll move around. I find the architects, there's a lot of I think there's a lot of architects who are interested in new architecture. And I have to say the UK, particularly London, has some of the best, what should I call, structural architects in the world. Mm-hmm. Per capita, better than anywhere. And so, I think it's a pretty fertile land. I know not everybody on the call is from in London or the UK, but still, these firms all have international reach. And so I think there's a pretty fertile group out there. You just need to get to them and convince them.
Mm-hmm. Do you think that intuition is structural engineers' worst enemy because it means that we repeat the mistakes of the past?
I think intuition can be educated. I think intuition is very, very powerful, and so my intuition's completely changed over the course of my career as I get the feedback. A lot of times I'll do some of my preliminary designs very, very simplistic, even by hand. Mm-hmm. And then, of course, we do all the analysis, and a lot of times because I've estimated the answer ahead of time, I know what to expect. And when the sophisticated computer analysis gives me a different answer, or gives me an answer, two things may happen. One is I'll confirm what I assumed, or I will learn something new. Mm-hmm. Because the computer gives me something different than what I expected. And over time, as this feedback loop, particularly from the computational tools, can move your intuition. But no, I believe in intuition, but you got to keep educating it.
Mm-hmm, mm-hmm. Okay. You mentioned a number of software packages. Do you think that these packages should be built by structural engineers, or is it the realm of computer scientists? If it's structural engineers, we're generally not experienced in the use of algorithms, software design, mm-hmm. and high-end computation. So do you think that this should be put in the essential skills, let's say, part of engineering exams at universities or, at a later stage at the professional career?
Yeah, well, do they need to be designed by, there's a lot of questions in that question. Do they need to be designed by engineers? I think probably kind of yes, even though we're not maybe the world's greatest programmers. Actually having someone who starts out in engineering, works for a while, and then goes away and gets a degree in computer science is not a bad career path. But having said that, I cannot tell you. First, I like to say building codes have the shelf life of banana. Computer programs, not much longer than a banana. Every program that everyone's using on this call today will probably be obsolete at some point in their career. And so, I don't think we should learn individual programs at all, but we should learn, how to use. Let me back that up. We should use what we have today available, and maybe learn the ones that we have today in school and like that, so you can do more. But don't make it a crutch for not understanding your profession. One of the most practical things in life is theory. In the distant future, we may be in the post-computational age. And so for the graduate engineers on the call, what is your value going to be in 40 years? And a lot of things will change, but the basic structural theory will not. And so the more you understand that the theory, the mathematics, so that when some super program from 20 years from now gives you a solution, you can answer the why. Why that's the answer, and that's going to be in my opinion, that's going to be the value of the structural engineer, is understanding the why of the solution that the computer gets us.
So, what do you see as the role of the structural engineer in the future?
I think it is that. First of all, it's the licensed professional. It's the person who protects the life and safety of the public, and but it is going to be less on the we used to call it dialing for beams. It's going to be less on sizing the members and that stuff, and more on the interpretation and understanding what possibilities are out there that are not being found. I enjoyed the presentation on the artificial intelligence about, it's how, it's the human ability to change the problem based on the input that you give and decide, okay, here's the solution, but let's not do this. Let's just change the problem.
One other question from our attendees is, do you think that Burj Khalifa could have been built in a more efficient way using today's advanced tools?
Could it be more? Let me say yes and no. Would I build it today the way I built it then? No. I learned things during the construction process that I would change. But basically, it's a giant beam coming out of the ground, and so in certain sense, no. In a few years, we might have accurate computational fluid dynamics. Right now, I don't trust computational fluid dynamics for structural forces. But so we did a lot of designing with the wind tunnel, so that as those tools become more readily available, there might be different design processes. But basically, the basic structural theory is, I think, solid, and then we'll stay with us.
Just a final question. We've got a few young engineers joining us and some students, and they are all asking about what advice could we provide to young engineers.
Okay, for really young people, my advice to people particularly coming out of school is, number one is stay poor, because until you get a lot of debt and own a lot of things, you have great freedom, the ability to go back to school or change professions or whatever you want to do. You can do that as long as you're not encumbered with a lot of debt. And so number one is stay poor. But if you're going to stay in structural engineering, learn as much theory as you possibly can.
Okay.
Both engineering mechanics, but also failures. Read about everything that ever fell down as best you can, and understand materials, understand the basics, because that will be good for your entire career.